Continuing our unknown coefficients discussion, say that our target function, g of t, is a polynomial, like this parabola here. And, well, then you want to guess another of that order polynomial. This one just says, let's do this example. It says solve. So I need both the homogeneous solution and the particular solution. So our step one then is just get the homogeneous solution. Well, I need my auxiliary equation, which would be lambda squared plus 3 lambda plus 2. Factoring that and solving for lambda, I get lambda equals minus 1 and minus 2, both negative real part, but I knew that because all of the coefficients are positive. So our homogeneous solution then is going to be a linear combination of our two little solutions. We're going to have some constant e to the first eigenvalue t plus some constant e to the second eigenvalue t. So I've got my homogeneous solution. I need to get my particular solution now and add it to my homogeneous solution. To get my particular solution, that's our next step. Well, unknown coefficients, I need to make a good guess here. So my target function is this parabola. So I'm going to guess another parabola. I'm going to guess it. So what people tend to do here then is guess an at squared plus b. Of course, this is a second order, so I need to guess the most general second order. So at squared plus bt plus c. I need the most general second order. So now we need to get our particular solution. Now our target function is a parabola, so I'm guessing the most general parabola, at squared plus bt plus c. Notice that, yeah, there's no t term in our target function, so I can think of it as like plus 0t if I would like. So anyway, I'm guessing the most general parabola. I need the derivative, 2at plus b, and I need the second derivative of my guess. And I'm subbing these three derivatives, the second derivative, the first derivative, and the no derivative, into the left-hand side and setting it equal to the target function. So I get y prime prime plus 3 times y prime, capital B, plus 2 times y is equal to my target function. And now I'm just going to equate powers of t. I've got 4t squared on this side and 2at squared on that side. That means that, and that's the only t squared on the whole left-hand side. So a has to be equal to 2. If I'm looking for coefficient in front of t, here I've got 6a t plus 2bt equals 0t. So I already know that a has to be 2, so this is 12t plus 2bt, so that means that b has to be minus 6. Lastly, just the constant terms. I've got 2a plus 3b from here plus 2c equals minus 2. I already know what a and b are. That tells me that c's got to be 6. So then my my particular solution is two t squared minus 6t plus 6. Now notice I did have initial conditions, and what do I do with initial conditions? I find the constants, but I did not jump right in and find them right away when I only had the homogeneous solution. I need to find the constants, I need to sub these conditions in to find the constants in the general solution. So let's find the general solution. The general solution is just the homogeneous solution. So this piece plus the particular solution. It's this general solution, the two pieces added together, that's where I sub in the initial condition. So the first one is y equals 0 when t is equal to 0. So when I sub t equal to 0, e to the 0 is 1, e to the 0 is 1, the 2t squared goes to 0, and the minus 6 goes to 0. So this is the equation that I get. I get one equation. Now let's get the next equation. The derivative of this function, so I'm differentiating that because I need to sub in the second equation, would be the minus would come down, here the minus 2 would come down, this would become a 4t minus 6, and in the derivative, when I sub 0 in, I get 0 out for the slope. So it starts at the origin. The solution starts at the origin with the slope of 0. Again, subbing in 0 here, e to the 0 is 1, e to the 0 is 1, and the 4t goes to 0. So here and here are my two equations, two unknowns. Now I go about solving these two equations, two unknowns, however you want to do it. Substitution, elimination, Kramer's rule, that's what I usually say. I think in this case, I'm going to just add this equation to this equation, so the C1s cancel out. One of this, and if I add those, let's just add those two equations together. If I do that, I'm getting 0 equals, the 6's cancel out, 0 equals minus C2, so C2 must equal 0. If C2 is equal to 0, then C1's got to equal to, going from this equation, minus 6. So now I've got my constants that satisfy my initial conditions. Here's the solution to this non-homogeneous differential equation that goes through the origin with a slope of 0. I guess the thing that I see most students, not most students, if a student makes a mistake in this type of question, it's oftentimes that they sub the initial conditions in too early. They calibrate the C1 and C2 here at the beginning and then add the particular solution to it. If I calibrate the C1 and C2 at the beginning with these y not equals 0, y prime not equals 0, check it out, try it, you'll get both c's equal to 0, which is wrong. Let's do another example. Well, this next example is, we're just finding the form of the particular solution. So the thing that we would sub in and then sub into the differential equation and then find the constant. So we're just concerned with the form here. Here my target function is e to the minus 2 times t. So I think my guess, well, would be a constant times that plus another constant times with the cosine. So I know that I need an e to the minus 2t, and if I differentiate that and differentiate it again, the e to the minus 2t part's not going away. The sine could become a cos, so I think I need both of these pieces. Now, is that a good guess? It is a good guess as long as as long as this isn't, or this isn't part of the, or I guess this would be then the homogeneous solution if it's a bad guess. But if it's a bad guess and that's a homogeneous solution, the eigenvalues would be complex. They would be -2 plus or minus I. So I need to check and see if the eigenvalues are not -2 plus or minus I. -2 plus or minus I would correspond to this being a homogeneous solution. So if I check the eigenvalues of this equation are minus I, or -1 plus or minus I, so -1, not -2. So this is all right. This is a good particular solution. That's the form. If the eigenvalues did match, so for instance, if I changed the question and made this a -1 instead of a -2, then what would I have to do? Well, we do the thing we do. Throw t's in front of here and try that out. Or if I'm not sure, I'm going to end up, or I'm not sure what to do in this case, after I watch the variation of parameters video, I'll have another way to find particular solution. Maybe I could use that form if the unknown coefficients is starting to get too complicated. Next example. Again, we're not finding the A's and B's. We could, it's tedious, but we could do it. If our target function is a polynomial, we guess the order of that polynomial. Well, now it's a polynomial times e to the 5th, e to the 5t, so our guess is going to be the most general polynomial, so squared. So this will be like our first example on that video. I want the most general second order polynomial, and I guess I'm going to need an e to the minus 5t tacked on it to match that piece. Now, do I need a constant in front of the e to the minus 5t? You don't, because if I did, I could distribute it over that a, b, and c, and it would get absorbed into like new a, new b, new c. That should be e to the 5t. I've got it right in the notes now, not e to the minus 5t. It's supposed to match. The e to the 5t and the e to the 5t are supposed to match. Also, missing a beard here. Next one, find the form. Ah, that's what I was hinting at here. I need this form, because remember the eigenvalues of this equation are -1 plus or minus I. So this would be the way the homogeneous solution. So I can't leave that as my particular solution. I got to throw t's in front here. Again, the eigenvalues are minus of the differential equation here are -1 plus or minus I. So because this is a because the eigenvalues, it looks like for this particular solution, are the -1 plus or minus I, we should not have this 2 in front here. The 2 is in the video. I took it out for the notes. This 2 shouldn't be here. It's a holdover, I think, from copy paste here. Let's think about our limit of the limit as t goes to infinity of the particular solution. So I guess to write this more mathy, what I'm thinking about in this case is the limit as t approaches infinity of the general solution. If both the eigenvalues have negative real part, then the homogeneous solution goes to 0, disappears, and the general solution is just the homogeneous solution plus the particular solution. If the homogeneous solution disappears, then the solution eventually approaches the particular solution. So this statement is only true if the eigenvalues have negative real part. So if the eigenvalues are negative, if they're complex, then this means the real part is negative. So in that case, the solution eventually approaches the particular solution. Now the particular solution might be zooming off to infinity, and then you say, oh, the answer is infinity. Yeah, but what the person wants when they ask the question, what does the solution eventually look like it is approaching, is they want to know what the equation, or what the solution is, they want to know what function the equation is eventually approaching, not the value. So even if the y particular is going to infinity, we can say the answer here is the y particular, because the homogeneous disappears. So what about higher order non-homogeneous differential equations? Well, here's the third order. I need to follow the same procedure. I need to get the homogeneous solution, then I need to add to that the particular solution. That gives me the general solution. If there are any initial conditions given, then after I get the general solution, at the end I can figure out the constants with those initial conditions. This cubic then, let's follow through the procedure. I need to find the homogeneous solution. So here's the auxiliary equation. The prime 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 is lambda cubed, the prime prime is lambda squared, the prime is 1 lambda, the no prime is no lambda. I can factor that equation and see that I get eigenvalues of 1, 1, and 3. Repeated eigenvalue and a real and different eigenvalues. So I'm going to get, this is a cubic, so I'm going to get 3 little solutions. So my homogeneous solution is going to be a linear combination of those 3 little solutions. Now this first eigenvalue of 1 would have a solution of just e to the 1 t. That second eigenvalue of 1, the repeated eigenvalue of 1, would be e to the t, but I need to throw a t in front of it because it's repeated. If there was 3 1s, then the next one would have a t squared in front. But I have a c3. Now let's take care of the third piece, and that would be e to the 3 lambda. So here's the piece of the solution that corresponds to the first one, the piece of the solution that corresponds to the second one, the piece of the solution that corresponds to the eigenvalue of 3. There's my homogeneous solution. Now let's get the particular solution. My particular solution, I need to use this unknown coefficients method. We're going to learn a second method, variation of parameters, has its own long video. But variation of parameters, the way we're going to learn it in that long video, is it only works for second order. So if I have a third order, we have to use unknown coefficients. So our target function here is a line, so I'm guessing the most general line. I need the derivative of that, which would be just a, and the second derivative is 0, the third derivative is 0. Sub all these derivatives into, just like we did before, sub all these derivatives into the left-hand side of the equation, and I get y prime prime minus 5y prime plus 7y prime minus 3y equals the target function. And let's figure out, that's supposed to not 50, but times 0. Let's figure out what the a and b have to be. Well, it looks like a has to be minus 3, so that the coefficient in front of the t's line up. If a is equal to minus 3, then let's look at the constant coefficients here. I get 7a, which I now know is minus 21, minus 3b has to equal 0, so b's got to be minus 7. So then our particular solution to this cubic is going to equal to minus 3t minus 7. So our general solution is equal to the homogeneous solution plus the particular solution. And again, at this point, if we had initial conditions, we'd need 3 of them. We could sub in those initial conditions and figure out what the C1 and the C2 and the C3 were.